So is it the screen sharing working for everyone? Hope so.
Yes.
Okay. So in today's session, we're going to look at the same example as last time, so the inverted pendulum, if you remember. So just to remind you, you have two axes of rotation, this alpha angle, which is the rod angle, and then the green angle, the theta angle, and you're only controlling this theta angle. You want to balance alpha, so that alpha is always close to 0, and still you want to be able to drive the system to any theta position. Theta angle is the reference that you should follow. Last time out of it, we derived the state space model in continuous time, then transform it in discrete time. So today I'm not going to do it again. I'm just going to reuse what we did last time. And then if you remember well, we then out of it designed a state feedback controller and then predictive and current observer. So today the idea is to do a little bit the same, but not using a state feedback controller, but instead an LQR controller. And we're going to see that an LQR controller, or a discrete LQR controller, also called dLQR, is nothing else than a state feedback controller, whereas the gain K is defined differently. It's not defined to ensure some closed loop pulse location, but defines differently. And finally, we're going to need, of course, an observer. And this time we're going to have a look at the minimum order observer. And I will just show you some a small comparison between this minimum order observer and the current and predictive observer we did last time. Okay, so let's start with it right away. So we have continuous time differential equation, and out of it already last time, so with the same sampling time of 10 millisecond. Okay, first and second question are rigorously the same as in exercise 1 of the session 7. So I'm not going to redo everything, but just reuse all these this discrete state space model that we found using the zero order hold method. So if I just open in MATLAB just to load the system, it's exactly the same as what we did last time. So a bunch of parameters, this matrix is M, A, and B, and then inverting M, and we can find the discrete system. Perfect. And so now the idea is to look at designing a discrete time LQR controller. So once again, the input is motor voltage, and the motor is driving the theta angle, so making the full structure rotating around the theta axis, and we want alpha to stay to 0 and theta to go to 1 dedicated position. The system is of course unstable, so the LQR controller should stabilize the system basically. So just to give you a little bit of, let's say, an intuition of what LQR is, already Alexis covered it in the lecture notes. So the idea is to reuse the Pontryagin minimum principle that some of you probably know. So just what you have to remember for this lecture is to understand where it comes from and how it works. Okay, then deriving all the mathematical equations is not that useful, let's say. So first, if we take a general case, Pontryagin minimum principle consists of one objective function. This objective function is a function j of the states and the inputs. Be careful because the j is defined as at each instant k, so k plus 1, and so on. And u here is the trajectory. So just take pen. So u that is here, it's a trajectory, okay, so it's not uk, but it's the full trajectory of u that we need to consider. And we need to consider the full trajectory of u because we wish to minimize this cost function in a predictive way. So that means that we want to find the full trajectory of u so that the kind of summation of each individual cost function are minimized. So the overall cost function that is here, this one here, is the summation of the contribution of each cost function at each sample time, basically. So here we're in discrete time, so it's just a summation. In continuous time should be an integral. And so in this cost function, there's basically one term called L here. This term is just saying, okay, for any states and any inputs at each sample time, I've got the cost, okay? And the cost of L is always bigger than 0, bigger or equals than 0. If it's not bigger or equal than 0, that means that my constant objective function can go to minus infinity, basically, and that's not possible, obviously. So at each sample time, this L function is a function of the current state, the current input, and the time, can be time variant, and it has to be bigger or equal than 0. And then there is a second term, because in Pontryagin minimum principle, it's a finite time control, let's say, a finite time trajectory. So you start at k equals 0 and you end at k plus n. So this is the last term, will be k plus n plus 1. And so you have some constraints on the final states. So here, for example, in our example, the final state should always be the theta angle that you expect and 0 for the alpha angle. Then we have the state equation. The state equation is potentially a nonlinear function of the states, the inputs, and the time, can be also time variant. In our case, of course, it's just a linear equation. We're going to see this in a second. And finally, out of this, if we want to minimize this, and this is a constraint in the form usually written like h of, or it's f of x, u, and time is equal to 0, because this is what you have if you make f minus xk plus I plus 1. Then this is really hard to solve because it's a cost function that is nonlinear and a state equation that is an equality constraint. And so to solve this a little bit easier way, let's say, in an easier fashion, you can design this Lagrange function. So Pontryagin minimum principle, usually we talk about co-states. Here in the lecture note, talk about Lagrange multiplier, but the idea is the same. That I'm still minimizing this, which is my objective function. And then I add this lambda term here, and this is the constraint. And this, if the constraint is always met, so if x of k plus I is always equal to f of xk plus I plus uk plus I plus k plus I is always equal to 0, then that means that my constraint is met. And so by the way, here it should be xk plus I plus 1. So here, this term equal to 0 is just because this is fulfilled, okay? And so if we wish to minimize the Lagrange function, then the constraint should always be 0, and we can still minimize the j function, and we have no additional constraint to consider. So to make things a little bit easier, the LQR method is first based on a quadratic cost function. So here you can see that this term here, which is nothing else than the psi I got here, is now quadratic. So it's x transpose times some square matrix times x, and L has to be positive semi-definite. And then this L term here is also a quadratic function with respect to x and with respect to u. So it's x transpose ux, u transpose ru. In here, we're considering a single input, single output. So r is a scalar. So this is just one value here. Sorry. This one is just one value. It's a scalar. If you have multiple inputs, it's just a matrix, but not mine. And we're also weighting the states with this Q matrix. Then the state equation is just the state space model we have, so it's already linear. And we can reformulate the Lagrange function. So it's exactly the same as above, but here I just replaced and plug everything in the quadratic cost function, and quadratics are not quadratic, but linear state equation. And so now if we want to minimize this Lagrange function, which implies that the state equation is fulfilled at each sampling point and the objective function is minimized, then we need to basically find the minimum of this Lagrange function. And to find the minimum, we have to take the derivative equal to 0, because we assume that it's convex. I mean, it is, you can verify it if you want. And so we need to find the partial derivative of L with respect to xk plus I and partial derivative of L with respect to uk plus I. And so if we do that, the problem is that we don't know what u is. So u will find a u like in a predictive control, for those who knows like MPC, stuff like this. U can be anything, it's a trajectory. And so here's the assumption we're going to make, is that u is a state feedback vector. Okay, so that means that u is equal to minus kx, and this is exactly the same as what we had last time with the ball placement method. Okay, so we're going to reuse exactly the same state vector feedback, so u equals minus kx, but trying to minimize this Lagrangian. And so to do that, we can formulate the so-called Rickett equation. You get all the details in the lecture notes. And we're going to look only at the steady state solution. So steady state solution means that n is taken as infinity. And so if n is taken as infinity, this is never reached. So basically I can remove this term. It's not useful anymore. And so I'm only considering this term here. I'm only minimizing this. So even the 1/2 is not really relevant. You can remove it. It's the same minimization in the end. And so this is what LQR is. So just to make a summary, and this is the only important point here is to really understand the summary, that LQR is based on Pontryagin minimum principle, which is something wider with the cost state and something quite complex indeed. And first, we're going to simplify it because we consider minimized quadratic cost functions. So all the term in the cost function is just quadratic terms with respect to the state x and the input u. We're going to consider linear state equation. Then we have no constraints. So remember that the state equation, this is a constraint, but it's already added to the Lagrange function with this Lagrange multiplier. So we got no additional constraints. So there's no constraints on u, for example, minimum or maximum u is not considered here. And then we're going to say that u is just a state feedback vector. So it's just minus k times x. This is an hypothesis. So it's probably not the optimal u, but it's sufficiently close to the optimal u, let's say. And finally, we say that k, so the gain k is constant. And the gain k is constant is because of this relation here. K is constant because we take an infinitely large horizon, and so n is equal to infinity. And so what you can see that this LQR method or discrete LQR method is strictly speaking the same as ball placement. The only difference is that it's a different method to define the gain k. Okay, so with LQR, the controller we have at the end is exactly the same as with ball placement, but the k gain is not defined to place or to decide the location of the closed loop poles, but it's defined to minimize this cost function here. Okay, and we've seen that this term is not here, so we're just minimizing the reference tracking and the input effort. So input effort is how much input we need, and reference tracking is how close we are to the reference value or to the desired value integrated over the trajectory. So making the summation at each sample time. So this is the most important things you have to understand today. If you understand this, basically everything else will look really, really simple. The only thing is you really have to understand that we're minimizing the reference tracking, the input efforts, that everything is to be quadratic cost function, linear state equation, there is no constraints, and we take u equal minus kx, that is probably not optimal, but close to optimality, and k is constant. So now if we move on, there's some requirements for this LQR design. The first requirements is that so-called stabilizability, and stabilizability means that if you have a linear state space model or state space system, all the uncontrollable eigenmods should be stable. Okay, so if there's an uncontrollable eigenmod that is not stable, we cannot apply LQR. If the system is controllable, okay, all eigenmods are controllable if the system is controllable. So we do not even need to look at stabilization or stabilizability. Stabilizability is only used when the system is not fully controllable, fully state controllable. Then we need to look at each eigenmods. If they are stable, they need, or if they are unstable, they need to be controllable. So if they're stable, they can be uncontrollable. It's not a problem because it's stable eigenmods, but every unstable eigenmod has to be controllable. So for example, here's a simple example. You have xk plus 1 is some matrix times xk. you can directly identify that this is a diagonal matrix. So these two entries are the eigenvalues. Then you make plus something times u, and you can directly see that the second state, so x2 in this case, x2 of k plus 1 is equal to 1.2 times xk, okay, plus 0 times uk. And so that means that x2 is only, x2, it's only a function of itself, basically. So x2 is only, will always increase. And so as x2 will always increase if x0 is 1 at the beginning, so x2 0 is 1, then that means that whatever u we choose, the system will be unstable. The second state will go to infinity. And so this is an example of a non-stabilizable system. For our system, we've already shown last time that it's controllable. So if it's full state controllable, that means that each state is controllable. So if we take, instead of taking states, we take the eigenmods. Remember that eigenmods is just some linear combination of the states, but they will all be controllable. So even if some eigenmods are unstable, they're all controllable, so it's perfectly fine. Now there's a second requirement for LQR design, which is called detectability. And so detectability means that if you take the two matrices J and Q, so J matrix is the state transition matrix here, and Q is the weighting matrix, so how much weight you put on each state in the cost function or in the objective function. Then it's called detectable. J and Q is a couple, or two matrices are called detectable if all the unstable eigenmods of J appear in the cost function. So what we expect is that if there's some unstable mod or unstable eigenmod of J, first they have to be controllable because of this proposition here. And then what we're saying is that in this product here, I need to make some positive weighting of this eigenmod, okay? If the eigenmod does not appear in this cost function, then they can be anything. They can go to infinity. We will never know that some states are going to infinity. So if there's an unstable eigenmod, it has to appear in the cost function. It has to be weighted in the cost function so that we can keep track of it and see if it's going to infinity, and then apply some control action to just bring him back to 0 to the reference. And so what that means is that we can take the eigenvectors, so vi here, and vi transpose and vi are just the eigenvector of J. So vi is just eigenvector of J. And so what we want is that vi transpose q, vi is bigger than 0, which is strictly speaking means that each eigenvector that corresponds to an unstable eigenmod has to appear in the cost function, so has to be non-zero. So here vi is eigenvectors of J for lambda I bigger than 1. So the norm of lambda bigger than 1 means that it's an unstable eigenmod. Okay, remember in discrete time, we can take the unit circle, and if there is a pole inside, it's stable, and if it's outside, it's unstable. So here we're only interested in these poles that are outside the unit circle. That means it's unstable eigenmods. So if we do this for our system, so lambda eigenvalue associated with vi, the eigenvectors, already said that. And so if we take just an example, so I just took the example from before. You can just have a look that I added the 2 here, so that this condition is, this is not true anymore. And so this condition, stabilizability, is met. So now we check detectability. Is this system detectable? And so we can look at, for some values of Q, remember that Q, we can define it. We are defining Q. So for some values of Q, for example, if I set 0 everywhere in Q, this will always be false, okay? Because if Q is 0 everywhere, this is always equal to 0, so it's not detectable. So that's why here I'm using a Q with at least one value. And so here, if I'm using this Q here, the system J here is already given in some kind of, it's a diagonal matrix. So you should all know that diagonal matrix, the eigenvalues are 0.5 and 1.2, and eigenvectors, I can write the first eigenvector and second eigenvectors like this, for example. And so if you compute this is like V2, this let's call it V1, then V1 transpose Q V1 is bigger than 0. Let's put it bigger than 0. And V2 transpose Q V2 will be always equal to 0 because V2 has only one element here. So it's going to multiply, it's never going to multiply this value here. So it's only going to use the zeros. And so if I'm using this Q here, the system is not detectable. Okay, but detectability is a little bit different than stabilizability, because stabilizability is only a property of the system, where detectability, I can transform or I can change the Q matrix such that the system becomes detectable. So here, if I set a 1 here, for example, instead of the 0, then the system becomes detectable. Okay, so remember that the system is to be detectable, and usually we can choose at least one Q such that the system is detectable. So if we look at our system, we can find the eigenvalues. I'm going to show you that in a second in MATLAB. It's just a EIJ common, EIG common. There's 4 eigenvalues. We've already seen that in session 7, if I remember well. And 2 of them are unstable, these 2. And so we need to make sure that for these 2 eigenvalues, there's some eigenvectors that correspond to these 2 eigenvalues. And so we need to make sure that this is detectable. So we found the associated eigenvectors. The first eigenvector is just the output, okay? And the second eigenvector is some combination of all the states. Now we can check a detectability condition, and we consider that Q. So Q, remember, it's a matrix. Q will be a 4x4 matrix, and the proposition I'm making here is to set all the off-diagonal element to 0. This is a classical way of weighting each state individually and not having some like weighting both states at the same time. So this is perfectly fine. This is the matrix I want to use with some values Q1, Q2, Q3, and Q4, and I want to know what I can do with these Qs. If I set all of them to 0, for sure, this eigenmod will be non-detectable, and so I cannot use LQR. So what are the requirements on this Q1 up to Q4 values such that my system is detectable? So if we take the first unstable eigenmod, that means that V1 transpose Q V1 is, simply speaking, is just Q2. So the first requirement is that this Q2 value has to be bigger than 0. And now if we take the V2 transpose Q V2, it's just a weighting of a diagonal matrix. So it's quite easy. It's just a scalar product, basically. And we can see that that means that the summation of all the Qs with some positive coefficient has to be bigger than 0. But if you remember, Q2 is already bigger than 0. So if Q2 is bigger than 0, I can choose any value I want for Q1, Q3, and Q4, and it will be perfectly fine. My system will be detectable because it's always bigger than 0. Last thing I forgot to mention, Q has to be, or I already said it before, but not, I can say it again because it's very important, Q has to be semi-positive definite. So here, if you take a diagonal matrix, that means that for any vector, V, you can call it X vector, or X is a state usually, not a good idea. Let's call it Xi. So for any vector, if I write this, okay, it should be bigger or equal than 0. This is what a semi-positive definite matrix Q means. And so that means that if it's diagonal, Q1, Q2, Q3, and Q4 has to be bigger or equal than 0. And so having only Q2 bigger than 0, because we know it's semi-positive definite, then I can choose Q1, Q3, and Q4 to any positive real value. Okay, so here, important point, Q2 has to be bigger than 0, and that makes sense because if Q2 is equal to 0, that means that I'm not weighting the outputs. And so if I'm not weighting the output is, there's an integrator in the output. If you look in the equation, that means that the input can grow and my system will just turn around its axis of rotation again and again. So let's go first to the MATLAB here. So to define these stabilizability and detectability criterions, so for stabilizability, I'm just using the controllability properties. So if we look at the rank of the controllability matrix, we did that last time. It's rank 4, so it's full rank. It's equal to n, and it's 4. We've got 4 states, so it's controllable. If it's controllable, it's stabilizable. Then I look at the eigenvalues and eigenvector that I can find with this common eigen here. So I got the eigenvectors 1, 2, 3, and 4, and the eigenvalues. And what I'm interested into is unstable eigenvalues. These two eigenvalues that corresponds to the two eigenvectors here, so the first column and second column respectively. Then what I did is I eigenvalue because diagonal of eigenvalues, I just keep all the eigenvalues as one vector instead of having a diagonal matrix, which doesn't change anything. And then I find the unstable eigenvalues. So, unstable eigenvalues are the first one and the second one. And then with this, I found the corresponding eigenvectors. So I will just keep the first and second eigenvectors, so first and second columns. And so I get the two unstable eigenvectors. Then I create with the symbolic toolbox Q1, Q2, Q3, and Q4, and I create basically the Q matrix with the diagonal entries, as we've seen in the PowerPoint. And then I just look at the condition. So condition is that this eigenvector, each eigenvector here, transpose times Q times the eigenvector should be positive, and that result in these two conditions here. So Q2 bigger than 0. And then some combination of Q1, Q2, Q3, Q4 with only positive term bigger than 0. And so as I know from the first condition that Q2 is bigger than 0, then I can choose Q1, Q3, and Q4 to anything but real or 0 value, because it has to be semi-positive definite. Okay, fine. So now that we have all the condition, all the requirements fulfilled, we can actually design the LQR controller. And so the LQR controller, if you remember, there's only two things left, which is the Q matrix and the R matrix. And so now we can have a look at how changing this Q and R matrix is affecting the system response. So if we go on MATLAB, the LQR is designed in MATLAB with a Q matrix. So here I'll just take a diagonal matrix with 1 everywhere. So each state is weighted with the same scalar value in this sense. So I'm not weighting the second or third state more than any other states, basically. And then some weight on the input. So the weight on the input R is a scalar value because there's only one input. And then in MATLAB, you directly find the K, so the gain K of our state feedback controller with this dLQR command, with the matrix, state transition matrix J, the H matrix from the state space model, and then the weighting matrices Q1R. And so if I run this one, I find some Q values, which is just my state feedback control, basically. And here, this P desired, this is the equivalent, or this is where the closed loop poles will be located. So in this case, for example, using these Q and R matrices, if you use the place command that we've used last time, remember, to place the poles with this pole location that more or less corresponds to nothing a priori, then we will find exactly the same gain. Okay, I can do it here. If I place this, I found exactly, you see, this gain here that we found with LQR is strictly speaking exactly the same as with pole placement. The only thing is with pole placement, I designed this controller to have these closed loop poles that corresponds to I don't know what, but with LQR or dLQR, this corresponds to minimizing the cost, the objective function we've seen, so the reference tracking and the input effort. And so the difference is that if I want to have more, if I want to use less input or having less input effort, I can plug in a 10, for example, here, and I can compute the gain. And so here's this new gain here, which corresponds to new pole location, closed loop pole location. Then with R equals 10, the system should react a little bit slower, and we should use less input action, basically. So if we have a look, instead of using this one, so this one should run, I can directly use the comparison one. So I can go back here anyway. So here I'm comparing using two different Q and R matrices. So the Q matrices is always identity, so it's one for each state. And then for the R matrix, so how much input effort I'm using 1 and 10. So for the solid line, it's 10, and for the dashed line, it's 1. And as you can see, if you're using an R equals 10, so if you're increasing R, then you can see here in the second graph, on this graph here, that the output, sorry, is now slower. So we want to reach 180 degrees starting from 0, and it takes more time to reach this value. And why does it take more time? Is that just because we have a higher input weight, and so that means that we can use less input. And so if we look at the input graph, this one here, you can see that the dashed line uses up to minus 2.5 volts and more than 1 volt, whereas the continuous line, which corresponds to R equals 10, is much more closer to 0, let's say. That means that we're less aggressive with the inputs when R is increased. The system is slower to react, but the input is lower in terms of norm, basically. And you can also have a look here. I've drawn all the costs. So the cost for X transpose QX and U transpose RU. And if I open it, MATLAB should be easier to visualize. So in MATLAB, I need to run this one. No, which one is it? Yeah, never mind. It's not on this. I can give you the file anyway. So here, if you look at the cost function, you see that the cost term with respect to the input, it's not really clear, but it's higher. So that means that because it's 10, even if we use less control action, the cost will be higher because it's 10 times higher. Now we can do the same with reducing R. So if we reduce R, the output is faster. So the system is kind of more, the controller is more aggressive. So the system is a little bit faster to reach the reference value, and the control action is a little bit higher. So here you can actually see it, but LQR compared to LQR with unit Q and R is a little bit higher. So that means that we're really using a lot of control action. If you remember here, we're going up to minus 2.5 volt in the input. If we set R equal to 0.1, so we kind of don't care of how much input we can use, then we're going to minus 5 volts. So it's way more aggressive. So this is about weighting this term here. Now we can also weight or change the weighting of the Q matrix. And so the Q matrix is responsible for the state tracking. So the first thing obviously we can do is only focus on the second state, because the second state is the output of our system. So it makes some sense to try to, as closely as possible, follow the output. And so if we set it to 10, so don't look at the absolute value. It can be 1, 10, 100. We don't care. It's just like we're multiplying it by 10, basically. Then you can see that the output is followed. Well, it's way faster to follow the real output or the expected output. The expected output is reached after, let's say, 2.5 seconds, where before it was taking around 7 seconds, for example. But to reach this output faster, let's say, then the control action is also much faster. So we need more to be really much more aggressive with the DC motor in this case. Then just another example. Here I'm weighting the first input, so the first state, sorry, so the first state, if you remember, it corresponds to alpha, which is the angle of the pendulum, and we want this alpha to be as close as zero as possible all the time. And so if we weight it here by 1 to the power 5, so 10 to the power 5 can be seen as quite a lot, but also be careful because it's not the same. I mean, the units are the same, it's radian or degree here and there, but here we're talking about a few degree, here we're talking about 100 of degree. So here, if I only set to 10, basically you don't see any difference. So here I have to increase it a lot to really see a difference. And so now you can see that the alpha angle is always really, really close to zero, but the output is followed, or it takes way more time to reach some desired output. and there's some overshoot also that you can see. And the input is somehow smaller than with Univ.LQR, because to keep alpha close to 0, I cannot have a really strong input. I need to do everything smoothly. Also, weighting only this first state, you have to be careful because it looks like it's almost discontinuous. You can also look into the input. It's like positive, negative, really fast, and so something I probably don't want. When you're weighting, if you want to weight alphas, then alpha stay to 0. Another possibility is to weight alpha dot instead. And so weighting alpha dot will bring alpha really close to 0 as before, but this time you can see that the control input is much smoother. So this is just to give you an overview. There's thousands of possibilities here. You just have to understand that you can weight each state individually. You can put more or less weight to each state. You can also weight the input. In terms of order of magnitude, you have to try. So here, for example, if you put 1 to the power of 5 to the second state, it's going to crash. It's not even going to work because it's way too much. But if you put only 10 here, it's mostly not weighting alpha dots as expected, because putting only 10 is not enough. So usually with LQR, you have to try and find the right order of magnitudes for each element here corresponding to the weights, to the states weighting, and the order of magnitude of R. So if I go on MATLAB, this is for the what I call the unit Q and R. So if you set all the Q diagonal Q entries to 1 and R equals to 1, then this is what you have. And what's interesting also here is to look at the cost, basically. So each time step you have a cost, and the cost is just the addition of each of these costs corresponding to alpha dot theta dot and u. And so if, for example, I increase u as I did in the first place, so I wanted to show it. So if I set 10, for example, then that means that I have to use less control action. And if we zoom in, you can see that now the control action u, it's not too much. It's clearly visible now that the control action cost, when R is equal to 10, it's this line here. This is for R equal to 10, and this was for R equal to 1. And so what you can see is that the control action, every time we're using some voltage to drive the motor, then the cost is significantly higher. And so obviously we're going to use less control action. And if we use less control action, most of the time that means that the system will act slower. And so here on this curve here, you can see that the output is slower. This one, once again, is R equal 10. And if we look at the inputs, you can see in this graph here that the inputs is like maximum, let's say 0.7 volts, where it was around 1.25 before. And in the negative part also, if I try to zoom in, it's also reduced. But this is how LQR works. You can see here that it's reduced. It's only going to -1 volt. Before it was going to -2.5. Okay. So it is LQR understood by everyone, at least how I can weight QR, what it corresponds to, how I can weight more, put more weighting on one state, another state, on the input, whatever, because this is the only thing you have to remember about LQR, is that we're not looking at some pole location, but we're going to try to have a more, let's say, intuitive calibration of our controller based on how close to the reference each state should be and how much control action we'll use. So this is everything I have to say about LQR. Also, we can add integration of the control error here. So we will have an additional state that we need to weight. So the Q matrix will be a 5x5. This is totally possible. And the last one to mention is that everything here is all the entries you put in Q and R are just relative to each other. So if I divide Q and I divide R by 10, for example, it will do exactly the same, because it's still minimizing this cost function, and it just corresponds to minimizing this times 1/10, for example. And so Q and R are always chosen with one another. So you need to find the right order of magnitude of both at the same time, basically. Okay, right. So if there's no question, we can now continue with designing a discrete time LQR with modal weighting. So the idea of modal weighting is that instead of weighting the states one by one, we're just going to weight the eigenmods of the system, so eigenmods of J. So to do that, the only thing that's changing here, everything is the same. The only thing that's changed is this Q matrix. Now I call it Q hat. So Q hat, instead of weighting the states, is weighting the eigenmods. And so to weight the eigenmods, we first have to find the eigen decomposition of the J matrix. Okay, so J has some eigenvectors and eigenvalues, n of them. And for the sake of simplicity, we're going to say that each eigenvector is each eigenvalue, is real number. If an eigenvalue is not a real number, that means that we need to change, make a change of basis, because it corresponds to kind of space of oscillation, let's say. But now we're going to only concentrate on real eigenvalues and eigenvectors. So what we can do basically is take this Q hat. So Q hat is supposed to weight the eigen direction, for example. So that means that Q hat is defined as V times Q times V transpose. And so this Q matrix here is just weighting each eigenmod, okay, or eigenvector. Can write eigenmod. So this Q matrix is weighting each eigenmod one by one. And so I'm going to look at, I'm going to design this Q matrix once again as a diagonal entry like this, Q up to Qn. And I directly going to multiply by V and V transpose, and that will define my Q hat row. Okay. And so the Q hat row is just when I'm taking X transpose times Q hat times X, I'm indeed taking X transpose V Q V transpose times X. And so I'm weighting the eigenmods directly. Okay. So instead of weighting the states, I'm weighting the eigenmods. This is the only difference. Then you can also already include this lambda matrix here. So square root of lambda 2 times. This is just to kind of have some pre-weighting on the mods. So for example, if you have two mods, one is as an eigenvalue of 1 and one as an eigenvalue of 10,000, then already if you take Q is equal to 1, 1 like this, then the first eigen direction is as the same weighting as the second one. If you're using this formula here, the first eigen direction is weighted by 1 if you're using this Q, and the second one is already multiplied by 10,000 because the eigenvalue is much greater, so it should be much more important. And finally, you need the Q hat to be symmetric, so that it's positive definite or positive semi-definite, and so you just take Q transpose times Q. And that's how you define this Q hat. And that's the difference with this Q hat row, what I call it row, that we're not sure that it's semi-positive definite. It should be, but because of some miracle approximation, for example, in MATLAB, it can be close to being non-positive definite, and that will lead to some problems. So to make it sure that it's symmetric, we're just using Q hat row transpose times Q hat row. And so if we have a look now in the MATLAB code here, so with modal weighting, once again, we found eigenvectors and eigenvalues, exactly as what we did last for detectability. Then we sort all the eigenvalues. It's not, usually you sort eigenvalues from the most important to the least important eigenvalues, but it's not the requirement. And then we sort also the eigenvectors. So now I end up with some eigenvectors that are ordered from the highest eigenvalue to the smallest eigenvalue. So this will be the first one, second one, third one, and first one. Here's the last one. So then I can define my new Q, and this Q here that I choose to 10, 1, 1 is 10 times the first eigenmod. So I'm going to put a weight on 10 of the first eigenmod, and 1 for each of the remaining eigenmods. So eigenmod second, third, and fourth eigenmods. Then I'm going to define this, should be Q hat, but as I'm using the same code, I'm not calling it Q hat, but this is definitely Q hat. Make it like this. And so I'm basically transforming this 10, 1, 1, 1 into the weighting of each eigenmod. As each eigenmod is corresponds to some eigenvectors, then this is my new Q hat matrix. And this Q hat matrix is doing nothing else than putting a weight on 10 to the first eigenmod and 1 to all the other eigenmods. Then I choose R equals to 1, why not? And I apply the LQR method once again. And if we have a look at the results, so once again, we can compare two strategies. The first one is LQR with unit, Q hat, and R. So these dashed lines means that each eigenmod is a weighting of 1 and R is a weighting of 1. And the solid line here, each eigenmod has a weighting of 1, unless the first eigenmod has a weighting of 10, and R is not changed as 1. And so as we know, the first eigenmod is, this is the first eigenmod. So it should be eigenvector first column. So the first eigenmod is some kind of weighting alpha dot quite a lot apparently, but alpha dot can also be small, so you have to be careful. And also weighting alpha. It's weighting just a little bit theta and somehow a little bit theta dots. And so if we look at this in the graph, we can clearly see that with a weight of 10, the system is faster. So that means that it is weighting theta a little bit somehow, but it's quite hard to see because the eigenmod is just a combination of the states, and the states have really different order of magnitude. Here it's around 100 for theta and between 0 and 10, let's say, for alpha. So this is what you end up if you weight the first eigenmod. If you want to have something different, you can try to weight different eigenmods, okay? If, for example, your system shows a really strong oscillation, undamped oscillation in open loop, then probably you want to weight a lot or put a lot of weight on the eigenmod that corresponds to this oscillation. Usually you have two eigenmods in this, if you have oscillation, but whatever, you want to put a lot of weighting on this oscillation. Here, there is no such oscillation apparently, so the first eigenmod, this is what you have if you weight the first eigenmod, basically. Can also try to put even higher. Probably you can see any difference if it's going to work. So it's too much. Okay, it's too much weight. So in the PowerPoint, I think I did exactly the same. So yeah, I was also weighting the first eigenmod. And so it's equivalent to strongly weight the derivative of alpha. And yeah, and also the theta. So it's mostly theta here. So you can see that this LQR with mod weighting is nothing else than an LQR, where instead of weighting X, we're weighting a linear transformation of X. So here we just basically defined it as, so here it will be Q hat. And so this is equivalent to X transpose times, let's call it T usually, it's T transpose Q T X. And T and T transpose in this case of modal weighting, it corresponds to transforming the state X into, or projecting the state X into the eigenvectors. But you can use any linear transformation you want, and it will work exactly the same. Here, modal weighting is just weighting some eigenmods. If you use something else, you can weight something else, basically. So this is how you can try to tune an LQR controller. Sometimes here, for example, it's better to, or it's easier to weight each state individually. Sometimes it's better to weight the eigenmods. So now, if you have no question, let's propose the first question for today. So let's imagine we have a discrete LQR. So we want to build a discrete LQR controller. The goal is to find the gain K, as we've just seen. So it's equivalent to a state feedback controller. And so you have to find the correct statements. The first statement is that there is no constraint on the control inputs. The weighting matrix R can be set to 0. So this is a proposition. B is that if a system is not controllable, the pole placement of the pole placement or the dLQR method cannot be used. So you cannot use pole placement if it's not controllable, and you cannot use dLQR. dLQR is just discrete LQR, so what we've just been seeing together. Third proposition is that the dLQR method is the preferred method to design K to meet the specifications such as a rise time or maximum overshoot. So if I give you, for example, in an exam, a system, I want to have some rise time of 10 seconds, maximum overshoot of 10%. Do you think that it's better to use dLQR over pole placement, for example? And the last statement is that for decreasing values or decreasing value in R, if it's single input, using the dLQR method, the closed loop poles will become faster. So now let me just open the poll. Here it is, and now it should work. So you can take a few minutes, couple of minutes to try to find, there's only one correct statement here that is proposed. Okay, so now almost everyone gave an answer. So for the remaining people, just try to just choose the one that looks the best one for you. It doesn't matter anyway. So I will just stop the poll and share the results now. Okay, so results are B and D. So let's take each statement quite rapidly. This is the first one. If there's no constraint in the control input, the weighting matrix R can be set to 0. This is wrong. This is really, really bad idea. Basically, if we try in MATLAB and see what's happening. So for classical LQR, if I set R to 0, I run the code, it's still working. So for this system, it is still working because the system is unstable and there's an alpha angle that should stay close to 0. But in general, if you remember, the J we try to minimize is X transpose QX plus U transpose RU. If this is chosen to 0, then what's happening is that you can use any U you want, even infinity in this case, because there's no constraints on U. And so the only thing that matters is following the state's trajectory or following the reference. So if we take a really simple system, I don't know, like xk plus 1 is equal to minus 0.5 x of k plus u of k. If for this system you set k r to 0, then what's happening is that u is infinite, because you want to go to the to reach the, it's not infinite, but it's going to be, it can be really large. It can be really large because you will just try to get to the right x in one sample. So it's not even worth using LQR anymore. You're just directly going to reach the reference. So never set R to 0. R can be set to really small values if you don't care, but never set it to 0. Then the second answer is, if the system is not controllable, the pole placement dLQR method cannot be used. This is true for pole placement, but not for dLQR. So pole placement, you need it to be controllable. dLQR, you only need it to be stabilizable and detectable. Okay. So stabilizable means that all the unstable eigenmodes should be controllable, but the stable eigenmodes is not necessarily controllable. We don't really care because it's stable. So if we cannot control it, it will inevitably go back to 0 because it's stable. The third answer was dLQR method is the preferred method to design K for specifications, and that's not true. I mean, you can intuitively try to reach some rising time, but you will need to iteratively test for a lot of Q and R matrices, whereas for pole placement, you just design a PT2 and it's way faster. And the last one is for decreasing value in R. Using the dLQR method, the closed loop poles will become faster. And once again, I have to do it again, never mind. So if you take X transpose QX plus U transpose RU, if R is increased or decreased? Decreased. So if I decrease R here, what's happening is that I do not care anymore about the control, how much control I'm using, but only following the reference. And so as I want to follow the reference and I'm summing over each sample difference, so at each sampling time, I define that I just wait here this X transpose QX, so I'm how far I am from the reference, then the system will inevitably become faster. In our case, it's not always getting a lot faster because also we can wait a lot alpha, for example, and want alpha to stay to 0 or close to 0. So it's just a general remark. If U is decreased, then the system will most of the time be faster or stay the same, basically. So this was the right answer. So now let's move to the last part for today. And the last part is about control observer. So last session, we designed 2 observers, which is current and predictive observer. And so we were using only one measurement, which is the output measurement. Today, we're going to say that we're lucky enough to have 2 measurements available, which is alpha and theta. And so the idea that each of these measurements directly correspond to a state. So we're measuring 2 states. It can also work if we're measuring not states, but having 2 measurements that is linear combination of states and are independent from each other. So just to keep it simple, let's say that we can measure 2 states. So if we can have alpha and theta, we can now split the state vector between something that we measure and something that is not measured, okay? So I call it XA and XB. So XA is alpha and theta, and XB is nothing else than alpha dot and theta dot. And so the observer will never try to build or to predict or estimate alpha and theta, but only estimate alpha dot and theta dots, okay? Remember that last time the observer was, we're observing theta, then we are having the observer, and the observer is going x hat. And in x hat was like alpha hat, theta hat, and so on. And this theta hat here is not necessarily equal to the measurements because the observer is estimating the states based on measurement. Here, for a minimum model observer, theta will be rigorously equal to the measurement. So the estimated alpha hat and theta hat will be nothing else than directly what we measure. So we need that the measure is not that noisy or is kind of filtered. And we'll see this problem in a second. So now we've split our system into 2 smaller states. So we just split the states. Then we can write 2 different equations. So we're just splitting J matrix and H matrix accordingly. And we can extract 2 relations. So XAK plus 1 is a function of XA of K, XB of K, and so on. And the same for XBK plus 1. And remember that these states are measured, so we do not need to model it. So here, x measured basically is equal to x hat, whereas here there is no measurement. So here we need this xb hat. You need to estimate it. So in this equation, there's only xbk plus 1 and xb of k that is unknown because we measure xa, we measure u, of course, and J and H are just matrices that we know it's a system matrices. Also, XAK plus 1 is not needed because as we will estimate XB of K, we will only need XA of K and XA of K minus 1, so it's perfectly known. So here the only unknown is XBK plus 1 and XB of K. If here I take XB of K to be approximately XB hat of K, so using the previous observation, we can see that we can build XB of K somehow. XB of K plus 1, sorry, can be estimated because everything else is known. And this is the idea of this minimum model observer. So the first equation can be written in this form. So I just putting XB on the left-hand side, and XB is now a function of everything else. And the second equation is kept as it was. And so here, we can define this second equation that now becomes the first one is equivalent to a state equation. So I've got xbk plus 1 is a function of something times xb plus something else in red. So everything else in red is known. It's kind of an input if you want. And we got an equivalent output equation. So this output equation is more or less like C transpose times xb, unless here C transpose is JAB, is equal to something else that is also known. And so if you remember last time when we were designing this predictive observer, we had the predictive observer state equation, which is just the system state transition equation, and an output equation, which is just our system output. And so now if we look carefully at all the colors, if we take the first equation, xbk plus 1 is equal to something times xb of k, and so jbb is more or less a state transition matrix associated with the unmeasured states, and everything is in red can be seen as h times uk. So the input, how the input is changing this state xb. Unless now this input is not only u, but it's everything else than xb. So it's u, and it's also our xa. So what I measured, the state that I measured, that can also change xb. And for the output equation, C transpose times xk is now JAB times xb, which is exactly the same. N is equal to m. M was the measurement. So here last time m was theta. And now m is all this thing because xa is measured and u is known. Okay. So if we do that, we can see that we do not need to derive everything, find where the closed loop poles are or whatever. We can just take a table and say J is now JBB, HUK is now JBAXA plus HBUK, and so on. We can just use some identification and reuse the proof from last time to design a predictive observer only for XP. And so predictive observer for a reduced state vector is called the minimum order observer. And so also take a look at this P gain here. It's not N by M now, it's N minus M by M. So to put it differently, this is now the number of element in XP, okay? So it's the cardinal of XP, whatever. So it's the size of XP if you want. Here it was the size of X, which is equal to XA and XB. So in a matrix form, XA and XB. So the only difference is that I can use exactly the same theory as before for predictive observer, but the matrices are now different. This is the only difference. And so if I want to find the equation for the estimation, so last time we used x hat of k, so we're estimating all the states. That was the equation. And now if I keep the same colors, basically, I can find xb hat of k. So estimating only the non-measurable part of the state vector. This is the equation. So it looks a little bit more difficult, but there's nothing more difficult. I still have, here are my closed loop poles, basically. So a function of the previous estimate. This, everything here is known. Okay, so it's just one value that is known, or it's just a vector that is perfectly known. And everything in blue also is known, and this is my gain. And so to define the gain, last time to define this P, we're just using pole placement for this. And so now we need to use pole placement for this. So once again, nothing has changed. If we quickly have a look, the P of full state, so the gain for the full state observer or the predictive observer, should have called it predictive. I mean, full state can be predictive or current. But here I'm using predictive observer. It was J transpose C and P observer. So using the place common in MATLAB. Now we can do exactly the same for minimum order, but this time we're using JDB. So only the part of J. When I've got X, K plus 1 is equal to J, XK plus BU or HU. Then J here is, remember, JAA, some JAB, whatever, and JBP. And so the only part that is of interest here is to look out the previous state JXB, sorry, is affecting the current state XB. That's all. And so we can find this, and we can take some pole placement for minimum order observer. We need only 2 poles. So last time we had minus 25, 26, 27, and 28 as a reference. Here I need only 2 poles, so I just take the 2 first poles, and I can define this pole into discrete time and then find the gain for the minimum order observer. This is the gain for the minimum order observer, and this is the equation I need to use in a Simulink. Okay. So if we have a look on MATLAB, it's really easy. As for the observer last time, minimum order observer, we just define all the matrices. So we just split this J matrix, so J matrix 4 by 4. JAA is 2 by 2. It's just this part. So the first square matrix, let's say on the top left corner. Then we got JAB, which is the top right. We got JBA, which is the bottom left, and JBB, which is the bottom right. We do the same for the H matrix. So H matrix is 4 elements, and the 2 first are HA and 2 second HP. Then we define our poles, and we can define our gain with the place common, and this is the gain for the minimum order observer using these poles. And so now to test it, so we can test it. I can also show you in Simulink. In Simulink, I got the observer here. Why is it not working? Okay, I can reopen it. So yeah, so I will show it later because apparently Simulink is not working. So I've got everything that is plot here, and it's okay. So this is a problem. Okay, now I'm gonna open it in PowerPoint. So if we have a look at the results, there's just some quick problem because some matrices are transposed or not depending on the MATLAB version. It's quite annoying, but it's just a transpose, so I will fix it before sharing it online. So using the minimum order observer, so here I'm comparing the no observer, so my states alpha, theta, alpha dot, and theta dot without observer is a blue line, so it's what I want basically, but I don't know. Last time we've already seen this predictive and current observer. We've already seen that because of nonlinearity, we have this kind of mismatch between the linear and nonlinear models. And now you can see that the minimum order observer is perfectly aligned. So minimum order observer is perfectly aligned for alpha here and for theta because we're directly taking the measured values. And here there is a small gap, you can barely see it. So it's much better because if the measurements are accurate, so without noise mainly, then you have only 2 states to build. And so as you have only 2 states to build, obviously it's way better and as estimating the states. So if we look in MATLAB, it works. Model observer, no, it did not worked. Where is Simulink? So the minimum order observer is here. First, I'm going to show you. So these were the predictive observer and the current observer from last time. And now we got the minimum order observer. So it looks a little bit like a mess, but it's nothing else than the expression that we've seen in PowerPoint. So we got the states, the previous estimate of XB here. So we take the previous estimate, you take unit delay, you feed it back with the gain JBB minus PGAB, which is our closed loop poles. And then you have some function of HUK minus 1 or equivalent of HUK minus 1 and equivalent of the measurement. And as you can see, the first part of the states, so XA, I call it XA, is directly taken from the observation, okay? So this is just the observation first and second state, and I'm directly feeding it back to the minimum order. Whereas for the predictive and current observer, you can see that here I'm taking the first state and second state, sorry, and still I'm kind of processing everything before creating the observation. So that means that the first state, the state that I observe, even if it's measured, the estimation is not the measurement. Here, all the states that are measured are directly taken as estimates. This is the only big difference between these two methods. Now, the thing is what's happening if we add some noise. And if we add some noise, as you can see, the measurement of theta and alpha is almost perfect because the noise are not that strong, and especially for alpha. Here you can see that as before for the predictive and current observer, when you have noise on alpha, on theta, sorry, then the alpha estimate is not as good as before, obviously. Now you can see that the minimum order observer is almost equivalent to the no observer method because the only difference between the purple and the blue line is the noise, and the noise is pretty small. You can, for example, see it a little bit here. So if the noise is small, then using minimum order observer is perfectly fine. Now what you can do is adding some much stronger noise. And if you had really strong noise, so here it's exactly the same as before, but there's strong noise in alpha, you can see that there's a big offset. So here's the problem is that you're taking the measurements and you say that the measurement is perfect. This is what minimum order is doing. So alpha and theta are not defined by the observer, they're just taking as a measurement. So if the measurement is not accurate, then the minimum order observer is not going to be good. And so here the main things to remember is every time you can add measurement to your observer, you can build a minimum order observer, and it should be better because you have more measurements, so you have more data coming into your observer. But you have to be careful. If the measurement is really bad, then there's whether you need to filter it in before, whether it's not going to work. And so here it's just the example. If you have really strong noise on alpha, it's better not considering alpha at all and using a predictive or current observer with only theta, because otherwise, so here's the problem is the variance of the noise, but also the fact that there's an offset. If I kind of take a filtered version for this purple line, so measurement with noise, I will basically have this, and this is an offset in the sensor. And every time you have an offset, even if the system is unstable on top of it, then it's not going to work for sure. So minimum order observer, you have multiple measurements, you want to take all the measurements, then minimum order observer is more accurate, let's say, it's better, unless some measurements are completely off track, there is a bias or really strong variance. So now let's look to the final question. So which statement is not a good reason to consider using a minimum order observer? First, there's multiple measurements are available. The real system, the plant, is nonlinear. The output measurement is not perfect. There's some noise. Two different sensors can be used in parallel to measure the outputs. So which of these statements is not a good reason to consider using a minimum order observer? Only one of these statements is true. And let me just restart the poll. Again, yeah, it should work. So based on what I've just said, according to you, what is the only statement that is not a good reason to consider minimum order observer? Okay, so now I got the results. So if I share the result as predicted, most of you answered the C. So let's first consider A. So multiple measurements are available, then it's a good reason to consider using a minimum order observer. We've just seen that. If the real system is nonlinear, if the system is linear with only one measurement, you can already build all the estimates, or you can already estimate all the states. So if the system is linear, usually having multiple measurements is only useful if some measurements are really bad, so really a lot of noise basically, but still it can be used. If the system is nonlinear, it's usually even more interesting to consider minimum order observer, because as the system is nonlinear and the observer is linear usually, then you know that sometimes, especially during transients, when you are not close to the operating points or close to the point where you linearize the equation, then it's better to have a minimum order observer. And the C answer is, here it's mostly wrong, basically. It's not a good reason. It's a good reason. It is a good reason, sorry. It's not a good reason only when you are adding a measurement that is really bad. So if I just go back a little bit here, remember that in this slide here, we already have noise on both theta and alpha. So there's already a lot of noise in alpha. You cannot see it, but here already you see there's some noise here. And as you can see, the minimum order observer is still way better than the predictive of the current observer, because you have two measurements. So even if there's some noise on both alpha and theta that you measured, if the noise is not completely crazy, it's still perfectly fine because you have more measurements, so more data coming in. So every time you have multiple measurements, even if there's some noise, usually it's okay. The only critical point is when you have really bad estimates. Here's the purple line on the graph of alpha is the measurement. And you can see that the sensor is really bad because here there's a really big gap. For example, here also, here it's really that I can even say here the sensor is not working properly. So it was in simulation, so I made it on purpose. But if a sensor is not working properly or doing some crazy, sending some crazy values, of course, it's not worth considering it. But most of the time, even if the measurement is noisy, it is better to consider minimum modal observer. So it was a little bit tricky here, but always if you have multiple measurements, take everything, even if there's some noise. The only case is if it's really, really bad. And so the wrong answer was the last one. Two different sensors can be used in parallel to measure the output. What it means, that means that here, for example, in our system, we got something like this x. So y is equal to theta. Okay. If now I give you two sensors, so sensor one will give theta one, an estimate of theta one, and sensor two, theta two. Can you build the minimum order observer out of it? And the answer is no, because minimum order observer means you have multiple measurements, but different measurements. If you're measuring, if you have two ways of measuring theta one and theta two, the only thing you can do is to build a theta measurement, let's call it Tm, that is a function of both. So can be, for example, theta one plus theta two over two, take the average. It can be some weighting between theta one and theta two, but you don't have two measurements here. You only have two times the same measurements, okay? So be careful to not, you need really to understand that you need two measurements that are different and that are giving different informations, basically. So if you have two sensors for the same output or same states measurement, then it's not a minimum modal observer. It's just you have two sensors and you need to kind of use these two sensors to have the output measurement. For example, you can have, I don't know, here it doesn't make sense, but sometimes some sensors are really good during transient, some sensors are really good during steady state. And so you have two sensors, one that is good when the output is almost constant, and one that is good during transient. And so you can use both values. And you will use mostly the sensor that is good in steady state when you're in steady state, and mostly use the sensor that is good during transient when you're in transient. And this is still a classical observer because you have only one measurement. Okay? So I guess that now this is clear because it's really important. And minimum modal observer can be usually way better than predictive or current observer, but only under these assumptions that you have different measurements that are measuring different things, and that the measurements are at least somehow accurate enough. So now let's make a quick conclusion that is really important because it's really the overall picture of control, most of the control. We've also seen a model following controller, we've also seen a dead bit controller, whatever, but most of the time you're going to use a state feedback control. And so for state feedback control, we've seen two methods for designing this K gain. So in session 7, we've seen pole placement. So we want to make sure the system is stable in closed loop. We want to meet some specification, and so to have a kind of PT2 behavior, let's say. And so you can define the rise time, overshoot, whatever. Today, we've seen that with LQR or discrete LQR, dLQR, then you are minimizing the cost function. So you are minimizing the states deviation from a reference and the input effort. It's suboptimal because it's, so if we consider a system is linear and cost function is quadratic, it's still suboptimal because u equals minus k transpose x is probably not the best control input we can have. And also we're taking k as constant. We're considering an infinitely large horizon. You have possible weighting of the open loop eigenmodes, so you can weight whether the states or the open loop eigenmodes or both if you want, or both. You have, if you have n states, you have n possibilities, so you can weight two eigenmodes and two states, for example. You can also do this. And so the goal is to say how much control effort you can have and how much weighting you put on each state or each eigenmode. And the second part is the observer. So x is not known, so you need an estimate. Usually estimate is x hat. Whether you use a full state observer, so predictive or current observer, you have only the output measurement that is available, or only output or one measurement that is available. Usually the output can be something else. And we've seen that system approximation during transient, if it's nonlinear, is not that good. And the observer pole location, we've seen if we take really fast poles, really slow poles, that if it's too slow, basically it's not matching the plant, so it's not working. And if it's too fast, then the noise is perfectly followed, and so that means the noise entered the state estimate. And today we've seen the minimum modal observer. So minimum modal observer is if you have multiple states that are observable, or if you have independent measurements that is a combination of the states basically, but independent. So if I got 2 times the same states, it's not multiple states observation, it's just 2 times the same states. It's better than the full state observer because you have more data coming in, you have already more than one state that you perfectly know, but it does not work when the measurement noise is really, really high, and only when it's really high. So most of the time, if the sensor is okay, let's say, then it's better, it's worth it considering minimal auto observer. If the measurement is really bad, but only sometimes, so sometimes you know it's really bad during transient, for example, and then you know it's going to be good again, then you can use, for example, a Kalman filter, but that's not part of the lecture. You can have a look online if you want. Kalman filter, I'm mentioning it here because these two observer here, okay, this is based on pole placement. So we're placing the poles of the observer, and so it's more or less equivalent to this, okay? Kalman filter in the other way, and you can have a look online if you want, it can be a good exercise. Kalman filter is more or less the equivalent of dLQR. So for Kalman filter, we're designing the observer gain, which is called P, if I remember well, such that we're minimizing the cost function. And what we're minimizing is x minus x at. Okay, so the integration or the summation, whatever. So this is just why I mentioned it here. So Kalman filter gives some, it's a little bit more robust because it's considering the uncertainty of the measurement. Okay, so that was the last session. There will be a session 9, but it will be covered by Alexis directly during the lecture. So now if you have any question regarding the exercise or regarding the homework, please let me know. You can also send me emails as usual. I'm trying to answer all the emails pretty quickly. You can also use the TUVille forum. And if you have no question, then this session is over, and see you this afternoon for the lecture.